Hi, my name is Daria, and I did my presentation on the paper called Detection and Characterization of Polydimethylsiloxanes in Biological Tissues by GC, AED, and GC-MS. In this presentation, first I'm going to talk about the goals of the paper and give a brief summary of what they used and their findings, and then I'll go into the background of silicon in biological tissues and why it's important to come up with a method that will detect siloxanes in biological tissues, and also what siloxane is used for in the medical field. Then I'll go into the aspects of the paper and I'll talk about GC, AED, and the methodology that the authors used, along with GC-MS, and then I will talk about the mouse liver extraction method that the authors used to compare PDMS in mouse liver and the different concentrations, and they looked at the percent recovery. Then I'll talk about the cyclic siloxane analysis and how the authors plan to analyze cyclic siloxane from breast implants, and then I will talk about the results of each of the methods, GCAD, then the GCMS, then the recovery that they got from the mouse liver, and then I'll talk about the cyclosiloxane results, and then I'll compare linear versus cyclosiloxane, which was an extension of the research that the authors decided to do. And finally, I'll wrap it up with some conclusions on the findings and further research that I will talk about. The goal of this paper was to validate gas chromatography methods that would identify and quantify polydimethylsiloxanes. Throughout the rest of the presentation, I'm going to refer to this as PDMS. For the first analysis, PDMS-V oil was used. This is the linear form of PDMS. Using two instruments to compare results, GC-AED and GC-MS were used to not only identify but to quantify the silicon. Some peaks were identified, and then some peaks also needed further analysis. The validation that was performed also established the limit of detection and percent recoveries of PDMS-V for all methods, including the mouse liver homogenates. After cyclosiloxanes were analyzed, the results compared to linear PDMS were done to see if there was any differentiation between the two and if the peaks overlapped. Silicone is a man-made polymer that is derived from the natural chemical element of silicon. Siloxanes are functional groups with alternating oxygen-silicon backbones. These are what are found in silicone. Silicone is the makeup of PDMS. PDMS was first synthesized in 1950. It was mainly made up of silicon and oxygen alternating bonds that have methyl groups attached to them. These methyl groups can be substituted by other groups, allowing organic groups to attach to inorganic groups. The silicones make PDMS thermally and chemically stable, along with being transparent, permeable, and hyperelastic. This allows them to be good candidates for prosthetics and cosmetics. Originally, siloxanes and PDMS were thought to be biologically inert. Some of the most recent studies show that it could be biologically toxic. It's important to know if this is going to be used for medical devices, whether or not it's toxic. Further research showed high amounts of silicon in transplant patients' tissues. Other instruments can only detect silicon and siloxanes, but cannot differentiate the two. That's why a new method to discover silicon percentages is very important. The top picture shows all the possible PDMS implants that are used, and then the bottom picture shows PDMS and the chemical structure, and you could see the silicone, oxygen, silicone, siloxane bonds with the methyl groups attached. I'm now going to talk about the methodology used by the authors, as well as how the atomic emissions detector works. The basic parameters of the column are listed here. They use an external standard of OPS because it closely relates to PDMS. Samples were prepped in ethyl acetate and then run through the GC. A capillary column was used with the following parameters: Emission was monitored at 251.6 nanometers because this is specific to silicon. 1 microliter of analyte was carried through the column with helium gas. Looking at the AED, the analyte comes out of the column and into a microwave-induced plasma chamber. There's a cooling system that is applied, and then the analyte is released from the chamber to hit a mirror that atomically emits toward a diffraction grate and then to a diode that collects the signal. Gas chromatography with a mass spectrometer attached was run under the following parameters. It's closely related to the parameters that were run for the GC AED, except the internal diameter is a little smaller and the injection temperature starts slightly higher. The samples were still prepped in ethyl acetate and run with an external standard of OPS. After the analyte is injected, it travels through the column to the mass spectrometer. So inside the mass spectrometer, it's then stopped at an ion source where it's ionized and fragmented. The fragments then transport through a mass analyzer that's held under vacuum so that everything doesn't just decompose. The smaller fragments will travel faster to the detector because they are lighter. The mouse liver extraction method was another aspect of the paper that the authors experimented with. They wanted to see if they could spike the liver with varying amounts of PDMSV concentrations. If they would get the same amounts back after being analyzed with GC AED and GCMS, then they know that they could further detect silicon amounts in human liver. They homogenized the liver using a rotary blade in 25 millimolar tris HCl buffer. 10% aliquots were then taken and incubated for 24 hours at room temperature after being injected with varying amounts of PDMSV. The PDMSV was extracted from the homogenates using ethyl acetate, which was then run on both instruments. They were looking at the percent recovery, which was calculated from the results. The last method used to identify and quantify PDMS looked at cyclosiloxanes directly extracted from breast implants. Here they monitored low molecular weight polysiloxanes. GC AED and GCMS were used again under the same original parameters. Here they looked at if there was a potential difference between the fragmentation and analysis of linear and cyclosiloxanes. If there was a difference, then they could see that in the presence of both linear and cyclic, that both could be determined. To the side, the pictures show an example of silicone and saline breast implants, along with 3 examples of cyclosiloxanes that are found in PDMS. Here we have the results from the GC atomic emission detector. In Figure A, it shows a chromatograph of the 12 silicon-containing peaks that were detected. Peak 1 had a retention time of 5.695 minutes. Then Figure B shows a snapshot of the emission spectra between 230 and 270 nanometers. As you can see, there's peaks at 250.7, 250.1.6, 252.4, and 252.8. These are all directly correlated to silicon and are important in the quantification of silicon. The level of silicon was quantified through the OPS standard. This is shown in Table 1. Out of the 91 nanograms of PDMSV, there was approximately 34.57% silicon detected. They were able to calculate this because of the PDMSV, there's 37.8% silicon. Figure C shows the tests run in sim mode to find the LOD for PDMSV. Using this, the GCAD established that there was an LOD as low as 80 picograms. The linear regression coefficient was greater than 0.99, showing that this is valid. Using GC with a mass spec detector, 12 peaks were again detected. The retention times of the mass spec peaks were close to those from the AED. 3 peaks were identified using Wiley mass spectra library. They were found to be dodecamethylpentasiloxane, which is shown in Figure B compared to the Wiley mass spectra, The second peak was tetradecamethylhexasiloxane, and then the third peak was hexadecamethylheptasiloxane. Peaks 4 through 12 were not identified through Wiley, so the authors used fragmentations from each peak to help identify it further. They knew that the predominant components of PDMSV are linear polymers of dimethylsiloxane with monomeric molecule mass of 74 AMU. Here they saw that all 12 peaks had the fragment containing these dimethylsiloxane polymers, along with other peaks at 147, 221, 281, 295, and 369 AMU. These fragments were the peaks used for the SIM mode. SIM mode was then used and scanned on these peaks to get figure C. The purpose was to quantify the selected ionic fragment peaks found from scan mode. What they were able to find was that the LOD was 10 picograms for PDMSV. Here the authors were looking at concentrations from 9 to 45 micrograms of PDMSV in mouse liver. They looked at the percent recovery corresponding to the first peak, which was the least abundant of PDMSV, and it's known as dodecamethylpentasiloxane. The percent recovery was found to be greater than 98%. A similar percent recovery was found using the GC, AED, and GCMS for the linear PDMS oil, being 96 to 98%. The graph shows that the low molecular weight silicone species can quantitatively be recovered from tissues using GC, AED, and GCMS. The concentrations can be detected at 1 microgram per gram of tissue or even lower. No metabolism or conjunction observed from the liver, but this could have been due to the freeze-thaw cycles that reduced the metabolic activity. If there was metabolism or conjunction observed, it could have interfered with the results. Again, using GC, AED, and GCMS, the authors used cyclosiloxanes to test for silicone content. In Figure A, it is the GC AED results, and Figure C is the GCMS results. As you can see, they look pretty similar, except they're just slightly different in retention times. 5 peaks were able to be detected in the mass spec, and that actually was all 5 peaks. They were corresponding to hexamethylcyclotrisiloxane, octamethylcyclotetrasiloxane, decamethylcyclopentasiloxane, dodecamethylcyclohexasiloxane, tetradecamethylcycloheptasiloxane. And in Figure B, there's a snapshot that was similar to the snapshot of the linear PDMSV oil. Again, you can see the peaks shown here are specific for silicon. When you compare the linear PDSV results, there's no linear peaks observed for cyclosiloxane. There you could see that there's no differentiation between cyclic and linear PDMS. Again, on the next slide, I'm going to go further into that. Here are the results for both GC-AED and GCMS when both linear and cyclic siloxanes were run together. The top is the results from the GC-AED, and the bottom is the results from the GCMS. The peaks that are that have the stars above them show the cyclosiloxanes, and the ones without it are the linear. There's no overlap between the linear and the cyclic siloxanes, so that there's clearly distinction, and further identification in the presence of both could be done for PDMSV. So some conclusions and takeaways of the paper include the validation of a method to identify and quantify PDMS. Detected cyclosiloxanes prove that low molecular weight polysiloxanes can also be detected and identified through both methods. GC-AED was able to give information about the organosilicon level, while also being able to quantify silicon content. GCMS was able to give specific information about the molecular structure to further identify each peak along with quantifying them. The final conclusion of this paper was that there is a detectable difference between linear and cyclosiloxanes when run on both GC-AED and GCMS. If I was to make a recommendation to the authors, or if I was to carry out my own further research, I would look at the human tissues of people with transplants and see if I could identify any silicon content. I would also spike human tissues and compare them to the mouse liver results to see if there was any similarities. To test for toxicity, I think that's also really important if this is going to be used for the medical field. I would look at the quantitative information and compare it to the lifespan to see if there's any possible toxic reactions through someone's life.